So today we're going to talk about second-order differential equations. So those are equations that involve a unknown function y, its first derivative, and its second derivative. We're going to look specifically at second-order differential equations which are linear on y, then homogeneous linear second-order differential equations. We'll look at the Wronskian, which is a way of checking for the linear independence of functions. And we'll look at Abel's identity and a procedure called reduction of order, by which, given a known solution to a second-order differential equation, we're going to find a way of coming up with a second linearly independent solution to the same differential equation. It's called a y2. Okay. So let's go ahead and start. Ignore all that. Okay, so second-order differential equation can be generally written as the second derivative of the unknown function is equal to a function of an independent variable, let's say x, and then y, and then y prime. And so this is not unlike the way we organize the first-order differential equations. Okay. Now, a special case this is where we have y prime being multiplied by some function of x, p, and then y is multiplied by some function of x cubed, and then we have plus another function that's called g. And if you move the negative terms to the left side, we can see that this is, in fact, we can define this as an operator on y, right? So plug y into this operator L, and this tells you exactly what to do. Now it's linear in y. So let's check. So and this is very easy, right? Because the linearity comes from the linearity of derivatives. You know, we can differentiate term by term. So if you have two functions, y1 and y2, and you plug it in here, you would get. And let's we know p is a function of the independent variable, so let's just simplify the notation. So here the argument is the sum of these two functions. And then by the linearity of differentiation, and you can distribute as well, you would just distribute rearranging we see that this is the linear operator acting on y1 plus the linear operator acting on y2. And you can also easily show that any multiple constants, not a function, but just a number, times the solution. You can easily show that as well, again, by properties of differentiation. So the left-hand side was a linear operator on y, so we call this a linear second order differential equation. So this is maybe the best analogy for is from linear algebra, where right here we have a linear operator acting on unknown function y is equal to some function on the right-hand side. This is analogous to the matrix, which represents a linear operator, times a vector, let's just call it, just for parallel, call it y bar, not a function, but a vector of coordinates, is equal to the right-hand side, let's call it b. Now, so that's so it's analogous to linear algebra, right? Now, furthermore, if we have the right-hand side over here, if that just is equal to 0, then we have a linear second order homogeneous differential equation. When the right-hand side function is 0, then we say we have a homogeneous. So this is again the same language as if in the matrix equation, the right-hand side was the 0 column vector, right? Okay. And also, if you recall, when we have a matrix equation like this, to find all the solutions to this, assuming they exist, we first find a vector, let's call it y sub h, h for homogeneous. We first find a solution to the homogeneous equation, and then you find a particular solution to the original equation. And then all solutions to the original equation can be written as the homogeneous solution plus the particular solution. And this works because if you multiply by a, matrix multiplication is linear, a times y sub h satisfies this equation, so that would be 0. And this satisfies the original, so that's b. There you go. Okay. So that's exactly how we're going to be approaching in general these second order derivatives, so second order differential equations. If they're non-homogeneous, so we have some function of independent variable on the right-hand side. We'll first find a solution to the homogeneous version of the equation. And then we'll find a particular solution to the original. So we'll learn tricks for doing that. And then all solutions can be written as the function which satisfies the homogeneous equation plus particular solution to the original. And then all solutions can be written as homogeneous plus particular. But that's the broad view. Now, another analogy to linear algebra here is when we find solution to a homogeneous equation, we want to find the null space of this matrix, right? So the set of solutions is the null space of this matrix. So all vectors such that A times Y is 0. And we, in particular, we're interested in finding a basis for the null space. And remember, a basis for the null space, well, a basis in general has to consist of linearly independent vectors, right? So we must have linearly independent vectors for our basis. It's part of the definition of being a basis. So likewise, if you have a linear second-order homogeneous differential equation, we're essentially looking for, here's our linear operator on y equals 0. So we're looking for all solutions to this equation, so we're essentially finding the null space of this linear operator. And so we want to find a basis for that null space. So we have to find linearly independent functions, right? So we want linearly independent functions. And generically, I guess we might as well say that we're going to have two-dimensional, right? Null space. So in the sense that we're going to try to find two linearly independent functions which satisfy that equation. And then a general solution will just be any combination. So C1 and C2 are numbers, arbitrary constants. So this would be a general solution. So a linear combination of the independent functions satisfying our equation will be a general solution to this homogeneous equation. Okay, so this idea of trying to find linearly independent functions that satisfy the homogeneous linear differential equation raises a question, well, how do you know whether two functions are linearly independent, right? Well, so let's investigate that. So how to tell whether two functions are linearly independent, and this is always on some interval. Okay. Well, we would start just like with vectors, right? So with vectors, if you had, let's say, v1 and v2, right? Two vectors. How did we check whether two vectors are linearly independent. Generally, right, so this is even for more vectors. With two vectors, it's kind of easy. Like just one is they're dependent if one is a multiple of the other. But the general procedure for checking or testing whether two things are linearly independent is to create a linear combination of the two vectors, set that combination equal to the zero vector. Next, you would solve for C1 and C2. The scalars in that combination. And if the only possible solution, right? So if you have a unique solution where C1 and C2 have to be zero, then we know that these vectors are linearly independent. Again, just to be clear, you can do this. You can use this procedure for more than two vectors. So otherwise, if we find some other solution for C1 and C2 where at least one of them is non-zero, then we know that the vectors are linearly dependent. Okay, so with functions, how do we check for linear independence in an interval? Well, you would actually use the exact same procedure, right? So you have a linear combination of the two functions. So C1 and C2 are scalars. Y1 and Y2 are functions, and that's equal to the zero function, if you will. So zero. And then you try to solve for C1 and C2. Now, these are y1 and y2 are differentiable functions. So let's just differentiate both sides here with respect to whatever the independent variable is. So you have constant times function, differentiate. Okay, right-hand side is 0. Okay. So now, notice that we can write this as a matrix equation. Where the matrix consists of functions. Yeah, we have y1, y2 in the first row, and then the derivatives of them in the second. Okay. So now you see that, yeah, we can now use linear algebra to solve for C1 and C2. And how do we know whether, and we're looking for, to get linear independence of the two functions, we're looking, we want the only solution for C1 and C2 be that they both must be zero. We're looking for a unique solution. Okay, so let me spell that out. So if y1 and y2 are linearly independent, so if the only solution, the unique solution here, is that C1 and C2 are both zero, then we say that the two functions are linearly independent. Again, we're going to look at the question of being on an interval. Well, but in which cases do we get a unique solution to this matrix equation? It's exactly when this matrix is invertible for right? So, and how do we know a matrix is invertible? So this matrix, which by the way is a function of an independent variable, right? Let's say x, just to be clear. So we get a unique solution if this is invertible. And an equivalent condition for a matrix to be invertible is to say its determinant is non-zero. It's not equal to 0. Okay. So that's actually going to be our test. So this is going to be a way to test whether two functions are linearly independent or not on an interval. Right, so if we compute that determinant and it's non-zero on a given interval, then we know that those two functions, y1 and y2, are linearly independent on that interval. So this has a name after a mathematician. So it's called the Wronskian, right? So let's define the Wronskian, and just remember it's a test for independence. I guess the mathematician was named Wronski or something. So the Wronskian of two functions of x. So let's just make that explicit. It's if this is a function of x, is the determinant that we presented here. Function of x. Okay. So if this Wronskian is non-zero on some interval, then we say that y1 and y2 are independent, linearly independent. Right. So let's take an example. So suppose that we want to know whether these two functions are linearly independent or not. So you would test by using the Wronskian. So we're going to test for linear independence. By using Wronskian. So we compute the Wronskian of two functions. So we have So let's write down y1 and its derivative, and then y2 and its derivative. Compute the determinant. And we see that our Wronskian is equal to an exponential function, which is positive, always positive there. So it's never zero. Right? So the Wronskian does not equal zero for all x's in this case. These two functions are linearly independent on the number line. Okay, so let's look at another example, and I'm just going to take a brief pause. Let's look at another example. So let's look at another example. Suppose you have two functions, let's say x and x squared. And we want to know whether these are linearly independent and on what intervals, right? So we would use the Wronskian as a test. So we have y1 and its derivative, y2 and its derivative. Compute the determinant. Okay. And you see that this is not zero as long as x is not zero. So we say that these y1 and y2 are linearly independent. On the interval from -infinity to 0, or and, I guess, I don't know. On 0 to infinity. Now, of course, we can very easily generalize this example. We have, suppose y1 is x to some power n, y2 is x to some different power m. So n does not equal m. These are going to be linearly independent. y1 and its derivative, and then y2 and its derivative. compute the determinant, and we see that since m and n are different, this is not 0. So this is not 0 as long as x is not 0. So we see that these kind of monomial terms, yeah, of a polynomial with different powers are linearly independent on either the positive part of the number line or the negative part of the number line. And you'll be, by the way, you'll be using Wronskian, right? So for more than 2 functions. So the Wronskian generalizes as a test for linear independence of multiple functions. So if you want to know whether 3 functions are linearly independent, you would create a combination of those functions so it's equal to the 0 function. And then we want to solve for C1, C2, C3, but it would be easier to do that if we actually look at derivatives as well. So we just differentiate both sides with respect to the independent variable once, twice, right? Because we want to end up with a system of 3 equations and 3 unknowns, the unknowns being C1, C2, C3. So we can get a square system in here. So this is rewritten as a matrix equation, where the matrix here is consists of the 3 functions and their derivatives up to the second derivative. And we know that if there's only a unique solution for the C's, namely that they're all 0, then we have linear independence. And we know that we have a unique solution as long as this matrix is invertible, and we know that this matrix is invertible as long as the determinant is not 0. So that determinant, it's not 0, guarantees linear independence of the functions, and that determinant for some reason gets a special name called the Wronskian. I'm just going to copy this 1 second. Ouch. Yeah. So that's the Wronskian. Again, so this Wronskian generalizes to arbitrary number of functions, right? Okay, let me check chat just in case somebody came in. Oh. Hello, Lana. Do you have a specific question? You can ask anything. You're the only one that's visiting here, so I'll make you a moderator. I don't think I'll be able to hear you if you're trying to use a microphone, but if you want to post in chat anything, I'll be happy to answer. And if you don't have any questions, then sure. So, yeah. So I am discussing the Wronskian. So as a test for linear independence. of functions on an interval. Okay. All right. So as long as this determinant is non-zero on some interval, we say that our three functions are linearly independent on that interval. Okay. So the related idea or identity, I guess, to using the Wronskian is called Abel's theorem, or identity. And so here we would have to have a second order linear differential equation that's homogeneous. And suppose we know y1 and y2 are independent functions that are solutions. To the differential equation. And we also have, say, an initial condition. So y at t naught should give you y naught. So Abel's identity then says, oh, well, I'll use x because I've been using x for independent variables. Okay. So we know that if we plug this into the Wronskian, we should get something non-zero, but this is going to be equal to a constant, which is the Wronskian evaluated at the initial value of our independent variable, and then times e to an integral from t naught to an arbitrary x naught to an arbitrary x. And what we're going to be integrating is this p, which is the function of x that multiplies y prime. I'll just use a dummy variable, let's say s, okay, for the integral. So that's Abel's identity. And I guess I won't indulge myself and try to prove it. Okay, but what I will talk about next is reduction of order. So this is a useful procedure by which, looking at the second order linear homogeneous differential equation again, and suppose you're given y1 and a known function that is a solution to the equation. You remember, well, as I mentioned before, but what we're looking for essentially is the null space of this linear operator. So we think of this as a linear operator on y. We prove that this is indeed linear is equal to 0, and so we're looking for all solutions to this equation. So we're looking for the null space of this linear operator, and in particular, we're looking for a basis. So we're looking for two independent functions. So given one function, which is a known solution to this equation, reduction of order allows you to find another solution, and so it's a second linearly independent from y1. to the homogeneous equation. Okay. And it's pretty simple. So this is the given function. What we assume is that there's another solution, which is a multiple let's call it u. So you have a function of the independent variable multiplying the known function, the known solution. So that's the assumption in reduction of order, so that we can find a second solution by simply multiplying the first one by some unknown function of x. Okay. And for short, I'll just write this as y is equal to u times y1. And to see how to find u, like we have, and we make an assumption and then we differentiate and plug it into the original equation to see what has to be true about u. So let's redifferentiate once. Product rule, and differentiate another time. A product rule in the first term, and plus, and then product rule in the second term. So we have y prime, and y double prime. Maybe I can rewrite this a bit. These two terms are alike, yeah. And then we plug that into our homogeneous linear equation. So we have y double prime plus, and then p times y prime. So p times and y prime is here. So and then we have q times y. And that should be equal to 0. Okay. So now we're going to rearrange. We're going to collect all the terms that you have a u in them. Okay. So those terms are here. There's here and here. So I'll write those first. Now, because all these terms will have a u in them, I can factor out u. Okay, that's that one, and remember I have to distribute the p here. So. Okay, and then plus the rest of it. So. Now notice what this is, right? Okay, the y1 solution to our homogeneous equation. So in other words, that should be equal to 0, right? Because y1 is the solution to that equation. So this is equal to 0. So that goes away, and we are left with this equation. What you notice is a second order differential equation in u. We have a u up to the second derivative there. But u is nowhere present. So you have u prime, double prime, and you have u prime, but there's no u. So it's actually a first order differential equation in disguise, right? Oops. So we can simply say let v equal to u prime for the time being. And now you see that you have a first order differential equation. So v prime would be u double prime. So we reduce this to a first order differential equation, and it turns out to be separable. So v prime, we're going to write as the derivative of v with respect to the independent variable. Let's say x. We can move everything over. I did something. Oh, I forgot y1. Crap. Okay. So let's first divide, assuming y1 is not 0, right? Let's just divide everything by y1. And then this is actually separable. So the v prime written that way. Bring all the other stuff to either side. You can factor out a v. Right? So v is common factor. So divide both sides by v. Multiply both sides by dx. Now you have to remember that y1 is known, right? So it's a known function of x, and p is a function of x. So this right-hand side is just all a function of x. So now we have two differentials that are equal. We know that we can anti-differentiate. I'm going to get log. I guess I should write absolute value of v. And here, if you integrate this thing with respect to x, of course, you can just use a substitution, but this should give you 2 times log of absolute value of y1. You can differentiate to confirm. Okay, so we're going to get, and of course, we'll just write that as where it's y1's being squared using properties of logs. And then this, since generically we don't know what this p is, right? We just leave it as an antiderivative. And I'm going to, I guess, up to a constant of integration, but we can ignore it. So then we exponentiate, and our solution is any multiple of the following. Properties of exponents. Let's use properties of logs to bring that power up here. So that would be y1 to the -2. And the exponential of the log are inverses, so you just get 1 over. All right. Well, we don't want to go through this procedure each time. So what we found is we were given a known solution to the homogeneous equation. We assumed that there's another solution that's simply some function times the known solution. And we found that v, or I guess I should say, remember what v is equal to u prime. So we found that u prime is equal to this expression, which is a very simple separable differential equation, yeah? Boy, it's terrible. And then so u can be found by anti-differentiating. And I'm ignoring, so there's 2 antiderivatives involved in this formula, but I'm ignoring the constants of integration because I'm just looking for some u that works. Okay, so there we go. Now we have a formula for the multiplier of the known function to give you a second linearly independent solution. Now, I haven't proven that it's linearly independent, so, but you can use the Wronskian for that. So we're going to have the Wronskian of y1, and the second solution that's independent we're claiming is u times y1. So we compute the determinant. Here's y and its derivatives. Okay, so these cancel. So as long as, guess, u prime isn't 0, right, so u prime can, as long as u prime is not 0, and just think about what that means. If u prime were 0, then u would just be a constant, right? But we're expecting to get a function. So as long as u prime at a given value of x is non-zero, then we have linearly independent functions. Okay. So maybe we can do an example of reduction of ordering. So suppose we have this differential equation, second order, and it's linear, and it's homogeneous, so equal to 0. And I tell you that this y1 is equal to e to the 2x, yeah? Okay. So indeed, that's a solution, y1 prime, y1 double prime. And so you plug it in, you get y double prime minus 4 times y prime plus 4 times y. So indeed, this is equal to 0. So this is a confirmed solution to that differential equation. So now, given that, we want to find another solution. So we want to find, let's call it y2, which is another linearly independent, another solution. So reduction of order says that we can assume that y2 is simply some unknown function u times y1. And without going through that messy procedure, we did derive a formula for u, and it was the antiderivative of fraction. The numerator was e to the negative power of p dx. This was the first solution squared in the denominator. So identify your p. So remember that we're looking at this conventional form for our second order linear differential equation here. So p, so once write it in the standard form, so the coefficient for y double prime should be 1. You identify p as the function that multiplies y prime. Okay, so p here would be the negative 4. Okay. y1 we said is e to the 2x. Okay, so we'll simplify the denominator, and we'll anti-differentiate in the numerator. And so you see that this is just 1. So u should be x up to a constant, of course. So now we find that y2, which is u times y1, is another solution to the equation, and it's definitely linearly independent. We proved it, but let's make sure that, good exercise with Wronskian, right? So we have y1 and its derivative. We have y2 and its derivative. We compute the determinant. Indeed, we have e to the 4x, which is always positive, right? So it's never 0. So indeed, y1 and y2 are linearly independent on the whole number line. The Wronskian is non-zero everywhere. Okay, are you sure you don't have any questions? Is it, Lana? I guess we can talk about how to actually solve a special case. Yeah, let's do that. So I don't know if you've covered this in class or not, but we were talking about second order differential equations, these linear ones that are also homogeneous. So there's a special case where P and Q are simply constants, right? So this is the constant coefficient case. And I'll write it like this. We'll see why in a second. So A, B, and C are simply numbers. Okay. How do we find solutions to this homogeneous equation? Well, we just if you have a linear operator on y equal to 0, and that linear operator consists of taking derivatives, so that's our linear operator on y, where we're going to be interested in a function called an eigenfunction, right? And it's going to be in the form e to the rx. Okay. So r is a real number, and we're going to assume that there's a solution that looks like this to our differential equation. Okay. And this function is special, right? The exponential function is special in the sense that if you differentiate it, you're going to get a multiple of it back. So what we're going to do, once we make this assumption about what a solution would look like to our equation, and we computed its derivatives as well, we can now just plug in. So a times y double prime. And then b times y prime. And c times y. So now notice that we have this e to the rx as a common factor. So that's, and it's never 0. Okay, so I'm not sure what that's supposed to mean. So not 0, right? So this has to be 0. And so that's called the characteristic equation for differential equation. Okay, so notice that we started off with a differential equation where you have a times y double prime plus b times y prime plus c times y equals 0. And so the characteristic equation is just a polynomial in this R, and it's analogous to the differential equation. So if you had a y double prime plus y prime, I guess, minus 6y, then if you assume that a solution has this structure, it's in the form of an exponential function, and you differentiate it once, twice, plug it in, you would get a polynomial in R. So this is 1 y double prime will kind of become R squared, y prime will become R, and then here you're going to get minus 6. So like y becomes R to the 0 if you wish. And that's a polynomial, right? It's a quadratic. We know very well how to deal with that. We would just use the, let's say, factor, or we would use the quadratic formula. Okay. So here, I mean, I don't have to use the quadratic formula because I can easily factor here. So we see that R would have to, the solutions here to this for R are, R is either -3 or 2. Those are the two solutions. So meaning that, like for a second order differential equation, we're looking for two independent solutions to the homogeneous equation, and indeed we get two different values of R, and since we assumed our solutions look like this, one of the solutions would be e to the -3 times x, and the other solution is e to the, now R is equal to 2, so 2x. Okay. And so so then all solutions, any solution to the homogeneous equation then, is simply a combination of those two. So that if you want to use analogies from linear algebra, right? We found two independent vectors, functions, and then any combination of them is also a solution to the homogeneous equation. Okay. So that's a general solution to the second order homogeneous equation. General because we have arbitrary constants. So I guess another example. So let's make this right now. What's interesting about this is that we know that when we're using the, we're finding solutions to a quadratic characteristic polynomial there, we don't have to get real numbers. So we can get complex numbers. So that's interesting. So let's do one. Like y double prime plus y is 0. So that's pretty simple. Let's make it 4y, yeah? So this is a second order linear differential equation with constant coefficients. Okay, so we can assume that solutions would look like e to some number r times x. And so the characteristic polynomial would become simply r squared plus 4r. Oops, sorry, 4. So y becomes just r to the 0 power. So here we see that r is going to be plus or minus I times 2. Right? We're taking the square root of -4, so we're going to get an imaginary I out of that. So it's completely valid to say that the two independent solutions to this equation are going to be e to the r1, so let's say, and then y2 would be e to the r2 times x. So that's valid, right? But you're going to learn that a lot of these differential equations have real valued solutions, and so this kind of disguises that fact because you have this I. So we can use one of Euler's identities, right? Because we don't want to have imaginary parts in something we know should be a real solution. Right? So the general solution we can say is a combination. So let's just call the constants A and B of these two. But we wouldn't leave it that way. We would actually use Euler's identity. So we get cosine 2x plus I a sine 2x. So this would be cosine of minus 2x plus I sine of minus 2x. Cosine is an even function. So cosine of a negative argument is the same as cosine of the positive version of that argument. But sine is an odd function, so this sine of a negative argument is the same as the negative of sine positive argument. Okay. So when using Euler's identity on this exponential, what we can do is we see that we have the real part involves just the cosine, so A plus B cosine. And then we have the imaginary part, so we have I and then A minus B times the sine 2x. So now A and B are arbitrary constants, right? So A plus B and A minus B are just new arbitrary constants. So we can then write this as C times cosine 2x plus, well, actually we're going to say I times A minus B is a new constant. Okay. So if we find that our roots of the characteristic polynomial are complex, we're gonna rewrite the answer in terms of sine and cosine. Okay. So if you have in general, let's do y double prime plus alpha squared, say y, is 0. Here's the characteristic equation. We know that the two solutions are that R is plus or minus I alpha. And so we can then either write I should have used beta for reasons. Oh well, it's okay. So these are the two solutions. But we want to have real valued functions here. So it turns out if you use Euler's identity, you can instead say that this is y1 might be, say, cosine of alpha x, and y2 would be sine of alpha x. So your general solution then is some combination of those. So when you have complex roots for your characteristic polynomial, you're going to rewrite the answer in terms of sine and cosine. Let's see. Okay, well, that's all I have. I think I went beyond what's on the homework, so I don't know if you've seen this in class, but thank you for joining me. I appreciate it, and I'm going to log out. Thank you so much.